Welcome to this comprehensive guide on continuity at a point. I'm excited to take you through one of the most fundamental concepts in calculus. Understanding continuity is absolutely crucial for mastering advanced topics like derivatives and integrals. Before we dive into the formal definition, think about what the word continuous means in everyday life. We use it to describe things that are unbroken, without gaps, or have a smooth flow. In mathematics, continuity has a very similar meaning. Here's a helpful way to think about continuity: the pencil test. If you can draw the entire graph of a function without lifting your pencil from the paper, then the function is continuous. If you have to lift your pencil because of a jump, hole, or break, then the function is discontinuous at that point. Understanding continuity is essential for several reasons. First, derivatives only exist at points where functions are continuous. Second, integration techniques work most reliably with continuous functions. Third, continuous functions provide the best models for real-world phenomena like temperature changes, population growth, and physical motion. Finally, continuity is a prerequisite for many advanced calculus concepts. In this comprehensive video, we'll start with the formal mathematical definition of continuity. You'll learn the three specific conditions that must be satisfied for a function to be continuous at a point. We'll explore different types of discontinuities you might encounter, work through detailed examples step by step, and discuss real-world applications. By the end, you'll have a solid understanding of this fundamental calculus concept. Are you ready to master continuity at a point? Great. In the next section, we'll dive into the precise mathematical definition and break down exactly what it means for a function to be continuous. This foundation will set you up for success in all the examples and applications that follow. Now we need to establish a precise mathematical definition of what it means for a function to be continuous at a specific point. This definition is fundamental to understanding continuity in calculus. A function f of x is continuous at a point x equals a if and only if three specific conditions are satisfied. These three conditions work together to ensure the function has no breaks, jumps, or holes at that point. The first condition states that f of a must exist. This means the function must actually be defined at the point x equals a. If there's a hole in the function at this point, or if the function is undefined there, then continuity fails immediately. The second condition requires that the limit of f of x as x approaches a must exist. This means that as we get closer and closer to the point a from both the left and right sides, the function values must approach the same finite number. The third and final condition states that the limit of f of x as x approaches a must equal f of a. In other words, the value that the function approaches as we get close to point A must be exactly the same as the actual function value at point A. We can express this definition mathematically using limit notation. The function f is continuous at x equals a when the limit of f of x as x approaches a equals f of a. This single equation captures all three conditions we just discussed. To better understand these conditions, imagine we're examining a function at a specific point. We need to verify each condition systematically to determine if the function is continuous at that point. First, we check if f of a exists by looking for the function value at point A. If we can find a specific y value for our x value of a, then this condition is satisfied. Second, we verify that the limit exists by checking that the function approaches the same value from both the left and right sides as x approaches a. Finally, we confirm that the limit value equals the actual function value. When all three conditions are met, we can confidently say the function is continuous at point A. It's crucial to remember that if any one of these three conditions fails, then the function is discontinuous at x equals a. All three conditions must be satisfied simultaneously for continuity to hold. Now we'll explore the epsilon delta definition of continuity, which provides the most rigorous mathematical foundation for understanding what it means for a function to be continuous at a point. The epsilon delta definition states that a function f of x is continuous at x equals a if the following condition holds. For every epsilon greater than 0, there exists a delta greater than 0, such that whenever the absolute value of x minus a is less than delta, then the absolute value of f of x minus f of a is less than epsilon. To understand this definition visually, imagine we have a function and we want to check continuity at a specific point. The epsilon represents how close we want f of x to be to f of a, while delta represents how close x needs to be to a. Epsilon controls the vertical tolerance, how far f of x can be from f of a. Delta controls the horizontal tolerance, how far x can be from a. The key insight is that for any epsilon we choose, no matter how small, we must be able to find a corresponding delta that makes the definition work. Here's how it works visually. The yellow vertical band represents our delta neighborhood around x equals a. The teal horizontal band represents our epsilon neighborhood around f of a. For continuity, whenever x is in the delta band, f of x must stay within the epsilon band. For our first example, we'll prove that the linear function f of x equals 2x plus 1 is continuous at x equals 3 using the epsilon delta definition. Step 1. We need to find f of 3. Substituting x equals 3 into our function, f of 3 equals 2 times 3 plus 1, which equals 7. Step 2. We set up the inequality. The absolute value of f of x minus f of 3 equals the absolute value of 2x plus 1 minus 7. Simplifying, this becomes the absolute value of 2x minus 6, which factors as 2 times the absolute value of x minus 3. Step 3. We need 2 times the absolute value of x minus 3 to be less than epsilon. Dividing both sides by 2, we get the absolute value of x minus 3 less than epsilon over 2. Therefore, we choose delta equals epsilon over 2. This completes our proof. For any epsilon greater than 0, we can choose delta equals epsilon over 2, and the epsilon delta condition will be satisfied, proving continuity. For our second example, we'll work with a quadratic function. We need to prove that f of x equals x squared is continuous at x equals 2. Step 1. First, we find f of 2. Since f of x equals x squared, f of 2 equals 2 squared, which equals 4. Step 2. We analyze the absolute value of f of x minus f of 2, which equals the absolute value of x squared minus 4. We can factor this as x minus 2 times x plus 2, so we get the absolute value of x minus 2 times the absolute value of x plus 2. Step 3. We need to bound the absolute value of x plus 2. If the absolute value of x minus 2 is less than 1, then x is between 1 and 3. This means x plus 2 is between 3 and 5, so the absolute value of x plus 2 is less than 5. Step 4. Now we can choose delta. Since the absolute value of x squared minus 4 equals the absolute value of x minus 2 times the absolute value of x plus 2, and we bounded the second factor by 5, we need 5 times the absolute value of x minus 2 to be less than epsilon. Therefore, we choose delta as the minimum of 1 and epsilon over 5. This choice of delta ensures that both our bounding condition and the epsilon requirement are satisfied, completing the proof of continuity. For our third example, we'll examine a piecewise function where continuity fails. The function f of x equals x when x is not equal to 2 and equals 5 when x equals 2. We need to determine if this function is continuous at x equals 2. Let's analyze this function. We have f of 2 equals 5 by definition. However, as x approaches 2 from either side, f of x approaches 2, not 5. Here's why the epsilon delta definition fails. If we choose epsilon equals 1, we need the absolute value of f of x minus f of 2 to be less than 1. This means the absolute value of f of x minus 5 must be less than 1. But when x is approximately 2, f of x is approximately 2, so the absolute value of x minus 5 is approximately 3, which is not less than 1. Therefore, we conclude that this function is not continuous at x equals 2. No matter what delta we choose, we cannot make the epsilon delta condition work for small values of epsilon. Let's summarize the key takeaways from our exploration of the epsilon delta definition. This definition provides the rigorous mathematical foundation for continuity. For linear functions, choosing delta as epsilon divided by the slope often works well. For nonlinear functions, we may need to bound terms and use the minimum of that bound in epsilon divided by some factor. When continuity fails, no delta will work for certain positive values of epsilon, as we saw in our third example. When functions are not continuous at a point, they can be discontinuous in several distinct ways. Understanding these different types of discontinuities is crucial for analyzing function behavior and will help you identify what's happening at problematic points. There are four main types of discontinuities we need to understand. Each type has distinct characteristics and mathematical properties that make them unique. First, let's examine removable discontinuity. This occurs when the limit of the function exists as x approaches a, but this limit does not equal the actual function value at that point. Here's a classic example. Consider the function f of x equals x squared minus 1 divided by x minus 1. At x equals 1, we have a hole in the graph because the function is undefined there due to division by 0. However, if we factor the numerator, we get x plus 1 times x minus 1 divided by x minus 1. The x minus 1 terms cancel, leaving us with f of x equals x plus 1, except at x equals 1, where the function is undefined. The limit as x approaches 1 equals 2, but if we define f of 1 to be some other value like 1.5, then we have a removable discontinuity. It's called removable because we could fix it by simply redefining the function value at that point. Next is jump discontinuity. This occurs when the left-hand limit and right-hand limit both exist, but they are not equal to each other. The function literally jumps from one value to another. Here's an example of a piecewise function. For x less than or equal to 1, f of x equals x. For x greater than 1, f of x equals x plus 1. At x equals 1, there's a clear jump in the function values. The left-hand limit as x approaches 1 is 1, while the right-hand limit as x approaches 1 is 2. Since these limits are different, we have a jump discontinuity. The function value at x equals 1 is 1, but that doesn't matter for the discontinuity. The third type is infinite discontinuity, also called a vertical asymptote. This occurs when the function approaches positive or negative infinity as x approaches the point of discontinuity. Consider the function f of x equals 1 divided by x minus 1. As x approaches 1 from the left, the denominator approaches 0 from the negative side, making the function approach negative infinity. As x approaches 1 from the right, the denominator approaches 0 from the positive side, making the function approach positive infinity. This creates a vertical asymptote at x equals 1. Finally, we have oscillatory discontinuity. This occurs when the function oscillates so rapidly near the point that no limit exists. The function values don't settle down to any particular value. A classic example is f of x equals sine of 1 over x. As x approaches 0, the argument 1 over x grows without bound, causing the sine function to oscillate more and more rapidly. Near x equals 0, the function oscillates between -1 and +1 infinitely often. No matter how close we get to 0, the function continues to oscillate, so no limit exists. To summarize, we have four distinct types of discontinuities. Removable discontinuities have holes that can be fixed. Jump discontinuities have different left and right limits. Infinite discontinuities approach infinity, creating vertical asymptotes. And oscillatory discontinuities have no limit due to rapid oscillation. Understanding these types helps you analyze function behavior and identify what's happening at points where continuity breaks down. Each type has its own mathematical signature and visual appearance on a graph. Now we'll explore specific examples of continuous functions. Understanding these common function types will help you quickly identify where functions are continuous and where they might have discontinuities. We'll examine three important categories. First, polynomial functions, which are continuous everywhere on their domain. Second, rational functions, which are continuous except where their denominators equal 0. And third, piecewise functions, which require careful analysis at the points where their definition changes. Our first example is a polynomial function. F of x equals x squared plus 3x minus 2. Polynomial functions have a special property that makes analyzing their continuity very straightforward. Here's the key insight. Polynomial functions are continuous everywhere on their domain. This means we don't need to check individual points. The function is continuous at every real number. Why is this true? Polynomial functions only involve addition, subtraction, and multiplication of x with constants. These operations preserve continuity. There's no division that could create undefined points, no square roots that could create domain restrictions. The domain is all real numbers, and the function is smooth everywhere. Even though we know polynomials are continuous everywhere, Let's verify this by checking continuity at a specific point, say x equals 1, to see how the three conditions are satisfied. First condition, f of 1 exists. We substitute x equals 1 into our function. F of 1 equals 1 squared plus 3 times 1 minus 2, which equals 1 plus 3 minus 2, which equals 2. Second condition, the limit as x approaches 1 exists. For polynomial functions, we can evaluate limits by direct substitution. The limit as x approaches 1 of x squared plus 3x minus 2 equals 2. Third condition, the limit equals the function value. We have the limit equals 2 and f of 1 equals 2, so the condition is satisfied. The function is continuous at x equals 1. Therefore, our polynomial function is continuous at x equals 1, and by the same reasoning, it's continuous at every point in its domain. Our second example is a rational function. F of x equals x squared minus 1 divided by x minus 1. Rational functions are quotients of polynomials, and they have different continuity properties than polynomials. The key insight for rational functions is that they are continuous everywhere except where the denominator equals 0. Let's find where the denominator is 0. Setting the denominator equal to 0, x minus 1 equals 0, which gives us x equals 1. So we need to examine what happens at x equals 1. To understand this function better, let's simplify it. First, we factor the numerator. X squared minus 1 equals x minus 1 times x plus 1. Now we can cancel the common factor of x minus 1 from numerator and denominator. This gives us f of x equals x plus 1, but only for x not equal to 1. At x equals 1, the original function is undefined. Now let's check continuity at x equals 1 using our three conditions. First condition, does f of 1 exist? Substituting x equals 1 gives us 1 squared minus 1 over 1 minus 1, which is 0 over 0. This is undefined, so f of 1 does not exist. Second condition, does the limit exist? Using our simplified form, the limit as x approaches 1 of x plus 1 equals 2, so the limit does exist. Third condition, does the limit equal the function value? Since f of 1 doesn't exist, this condition cannot be satisfied. Since the limit exists but the function value doesn't, we have a removable discontinuity at x equals 1. We could remove this discontinuity by defining f of 1 to equal 2. Our third example is a piecewise function. F of x equals x squared if x is less than 1, and 2x if x is greater than or equal to 1. Piecewise functions require special attention at the boundary points where the definition changes. For piecewise functions, we need to check continuity at the boundary points where the function definition changes. In this case, the boundary point is x equals 1. Let's check our three conditions. First, does f of 1 exist? Since 1 is greater than or equal to 1, we use the second piece of the function. F of 1 equals 2 times 1, which equals 2. Second condition, does the limit as x approaches 1 exist? For piecewise functions, we need to check both the left-hand and right-hand limits. The left-hand limit as x approaches 1 from the left uses the first piece. Limit of x squared as x approaches 1 from the left equals 1 squared, which equals 1. The right-hand limit as x approaches 1 from the right uses the second piece. Limit of 2x as x approaches 1 from the right equals 2 times 1, which equals 2. Since the left-hand limit equals 1 and the right-hand limit equals 2, and 1 does not equal 2, the overall limit does not exist. Therefore, the function is not continuous at x equals 1. Since both one-sided limits exist but are not equal, this is called a jump discontinuity. We've now seen three important types of functions. Polynomial functions are continuous everywhere. Rational functions are continuous except where their denominators are 0. And piecewise functions require careful analysis at their boundary points, where different pieces of the function meet. Now that we understand what continuity means, we need a systematic method to check whether a function is continuous at any given point. This step-by-step approach will become your reliable toolkit for analyzing continuity. To determine if a function is continuous at a point x equals a, we follow three essential steps. Each step must be completed successfully for the function to be continuous. Step 1. We must verify that f of a exists. This means the function is actually defined at the point we're checking. If the function is undefined at x equals a, then it cannot be continuous there. Step 2. We need to find the limit of f of x as x approaches a. This limit must exist for continuity. Sometimes this requires checking both left-hand and right-hand limits, especially for piecewise functions. Step 3. We compare the limit from step 2 with the function value from step 1. If the limit equals f of a, then the function is continuous at x equals a. If they're not equal, or if either doesn't exist, the function is discontinuous. For our first example, we have a polynomial function f of x equals x squared plus 3x minus 1. We want to determine if this function is continuous at x equals 2. Polynomial functions are generally well-behaved, but we'll apply our systematic approach. Step 1. We need to check if f of 2 exists. Since this is a polynomial, we simply substitute x equals 2 into our function. F of 2 equals 2 squared plus 3 times 2 minus 1. This gives us 4 plus 6 minus 1. Therefore, f of 2 equals 9. Since we got a real number, f of 2 exists. Step 1 is complete. Step 2. We need to find the limit of f of x as x approaches 2. For polynomial functions, we can evaluate limits by direct substitution since polynomials are continuous everywhere. The limit as x approaches 2 of x squared plus 3x minus 1 equals 2 squared plus 3 times 2 minus 1, which is the same calculation we did before. Therefore, the limit as x approaches 2 of f of x equals 9. The limit exists. Step 2 is complete. Step 3. We compare our results. The limit as x approaches 2 of f of x equals 9, and f of 2 also equals 9. Since the limit equals the function value, all three conditions for continuity are satisfied. Therefore, f of x is continuous at x equals 2. This confirms what we expect for polynomial functions. They are continuous at all real numbers. For our second example, we have a rational function g of x equals x squared minus 4 over x minus 2. We want to check continuity at x equals 2. Notice that the denominator becomes 0 when x equals 2, which suggests potential problems. Step 1. We check if g of 2 exists by substituting x equals 2 into our function. G of 2 equals 2 squared minus 4 over 2 minus 2, which gives us 4 minus 4 over 0. This results in 0 over 0, which is an indeterminate form. Since we cannot evaluate this directly, g of 2 does not exist. However, we should continue with our analysis to see if there might be a removable discontinuity. Step 2. Even though g of 2 doesn't exist, we can still find the limit. Since we got 0 over 0, this suggests we might be able to factor and simplify. We factor the numerator, x squared minus 4 equals x minus 2 times x plus 2. So our function becomes x minus 2 times x plus 2 over x minus 2. We can cancel the x minus 2 terms, giving us g of x equals x plus 2, but only for x not equal to 2. Now we can find the limit. The limit as x approaches 2 of g of x equals the limit as x approaches 2 of x plus 2, which equals 2 plus 2, or 4. Step 3, we compare our results. The limit as x approaches 2 of g of x equals 4, but g of 2 does not exist. Since the function value doesn't exist, we cannot have the limit equal to the function value. Therefore, g of x is discontinuous at x equals 2. However, since the limit exists, this is called a removable discontinuity. We could make the function continuous by defining g of 2 to equal 4. For our third and most complex example, we have a piecewise function. H of x equals x squared if x is less than 1, and 3x minus 2 if x is greater than or equal to 1. We need to check continuity at the boundary point x equals 1. Step 1. We check if h of 1 exists. Since 1 is greater than or equal to 1, we use the second piece of our piecewise function. H of 1 equals 3 times 1 minus 2, which equals 3 minus 2, or 1. So h of 1 exists and equals 1. Step 2. For piecewise functions, we must check both left-hand and right-hand limits to see if the overall limit exists. The left-hand limit as x approaches 1 from the left uses the first piece, x squared. This gives us the limit of x squared as x approaches 1, which equals 1. The right-hand limit as x approaches 1 from the right uses the second piece, 3x minus 2. This gives us 3 times 1 minus 2, which also equals 1. Since both one-sided limits exist and are equal, the overall limit exists and equals 1. Step 3, we compare our results. The limit as x approaches 1 of h of x equals 1, and h of 1 also equals 1. Since the limit equals the function value, all three conditions for continuity are satisfied. Therefore, h of x is continuous at x equals 1. This shows that piecewise functions can be continuous at boundary points when the pieces connect smoothly. We've now seen how to systematically check continuity using our three-step method. Remember, check if the function value exists, find the limit, and compare them. This approach works for any type of function and will help you identify exactly where and why discontinuities occur. Continuity might seem like an abstract mathematical concept, but it actually has incredible practical applications in many fields that affect our daily lives. From the music we stream to the movies we watch, from financial markets to medical diagnostics, continuity plays a crucial role in making these technologies work smoothly and accurately. Our first application is signal processing, which is fundamental to digital communications and audio technology. When you stream music or make a phone call, digital signals need to be reconstructed from discrete data points. These discrete points represent digital samples of an analog signal. To reconstruct the original continuous signal, we need the mathematical concept of continuity. The reconstruction process creates smooth curves that connect these points in a mathematically consistent way. In computer graphics and animation, continuity is essential for creating smooth, realistic motion. When animators create character movements or camera paths, they use mathematical curves that must be continuous to avoid jarring jumps or discontinuities. Compare this to a continuous, smooth animation curve. Notice how the continuous path creates natural, flowing motion without any sudden jumps. This is why continuity is crucial in creating believable animations and smooth user experiences. In financial markets, continuity assumptions are fundamental to algorithmic trading and risk management. Stock prices and market data are modeled as continuous functions, even though they're actually discrete transactions. This continuous model allows traders to use calculus-based techniques to analyze trends, calculate derivatives for risk assessment, and develop sophisticated trading algorithms. Without continuity assumptions, many of these mathematical tools wouldn't be applicable. Our final application is medical imaging, where continuity plays a crucial role in image reconstruction. When you get an MRI or CT scan, the machine collects discrete data points, but the final image must be a continuous representation of your body's internal structures. Continuity constraints ensure that the reconstructed image is smooth and realistic, without artificial discontinuities that could be mistaken for medical abnormalities. This mathematical principle helps doctors get clear, accurate images for diagnosis and treatment planning. As we've seen, continuity is far from being just an abstract mathematical concept. It's a fundamental principle that enables countless technologies we rely on every day. From the smooth playback of digital music to the accurate diagnosis of medical conditions, continuity helps bridge the gap between the discrete digital world and the continuous physical reality around us. Now that we've explored continuity in depth, it's crucial to understand the essential tips and common mistakes that students encounter. These insights will help you master continuity problems with confidence. First, here are the essential tips you should always remember when working with continuity problems. Always check all three conditions for continuity. The function must be defined at the point, the limit must exist, and the limit must equal the function value. When dealing with piecewise functions, be extra careful to evaluate the correct piece of the function at the point in question. Use graphing tools and technology to visualize functions and identify potential discontinuities before doing algebraic work. Don't rely solely on the pencil test. Just because you can draw a function without lifting your pencil doesn't guarantee mathematical continuity. Now let's examine the most common mistakes students make when working with continuity. The first and most dangerous misconception is the pencil test. Many students believe that if they can draw a function without lifting their pencil, then it must be continuous. However, this is mathematically incorrect. Consider this piecewise function where f of x equals x squared for all x not equal to 1 and f of 1 equals 3. Visually, this function might appear continuous, but mathematically it has a removable discontinuity at x equals 1. The limit as x approaches 1 is 1, but the function value is 3. This is why we must always verify continuity algebraically, not just visually. The second common mistake occurs with piecewise functions. Students often use the wrong piece of the function when evaluating at the boundary point. Consider this piecewise function g of x. To check continuity at x equals 2, we need to evaluate g of 2. The wrong approach would be to use the first piece, giving g of 2 equals 2 times 2 plus 1, which equals 5. The correct approach recognizes that since 2 is greater than or equal to 2, we must use the second piece. Therefore, g of 2 equals 2 squared, which equals 4. Always carefully check which condition the point satisfies before selecting the appropriate piece of the function. The third common mistake is not checking all three conditions for continuity. Some students check only one or two conditions and incorrectly conclude the function is continuous. Remember, for a function to be continuous at a point, all three conditions must be satisfied. First, the function must be defined at the point. Second, the limit as x approaches the point must exist. Third, the limit must equal the function value at that point. All three conditions must be satisfied simultaneously. If even one fails, the function is discontinuous at that point. Now let's discuss best practices for mastering continuity problems. Use technology like graphing calculators, Desmos, or GeoGebra to visualize functions and identify potential problem areas. Always work systematically through all three conditions for continuity. Don't skip steps or assume conditions are satisfied. Double-check your algebraic work, especially when evaluating limits. Small errors can lead to incorrect conclusions. Practice with various types of discontinuities to build your intuition and recognition skills. Whenever possible, verify your analytical answers by graphing the function to see if your conclusions make visual sense. To summarize the key takeaways from our discussion of tips and common mistakes, always check all three conditions for continuity systematically. This methodical approach prevents errors and ensures accuracy. Don't rely on visual tests alone. Mathematical rigor requires algebraic verification of continuity conditions. Exercise extra caution with piecewise functions, ensuring you use the correct piece for each evaluation. Use graphing technology to support and verify your analytical work, but never as a substitute for mathematical proof. By mastering these concepts and avoiding these common pitfalls, you'll be well equipped to tackle continuity problems in calculus and beyond. Remember, practice and careful attention to detail are the keys to success in mathematics.